a delta connected load, each phase of which has a resistance of 15 ohm and an inductive reactance of 20 ohm. The line voltage is 400 volt. Calculate the current supplied by the current supplied by the alternator and the output power and kVA rating of the alternator, neglecting any losses in the line between the alternator and the load. Okay. All right, so the current supplied by the alternator would have been a line current, right? Right? Since it's a star connected machine, so the current on the lines would be a line current. All right, so let us. Yeah, sorry, I interrupted you.
No, I'm saying it's a line current, sir.
Okay.
The
All
current
right.
supplied by the output.
Good, good, good. All right, so let me bring up the solution then. All right, so this is what the circuit looks like, right? So a three-phase star connected alternator. Alternator is another name for a three-phase synchronous generator. All right. So you have the three phases. Star connected. The windings are mostly inductive, but there's also some resistive elements. So I just draw since it's mainly inductive, I just draw the inductive part. But bear in mind, when we get to drives 2, that the windings also have some resistive component. All right, so the lines feeding from the generator are coming out like this. So the red, the yellow, and the blue lines. All right, then a delta connected load now is connected to the lines, right? So this is my delta connected load. All right, it's a balanced load because in each phase you have 15 ohm resistance and 20 ohm inductive reactance, right? So it's a balanced load. So when you work out that impedance, it is 25 angle 53.13. All right. Now, since the load is our primary focus, I use in the voltage, the phase voltage at the load as my reference voltage, right? All right. So the reference phasor here is for the delta system is VRY. So VRY is at 400 angle 0. All right. And since the load is balanced, we only need to consider one phase. All right. So I find the current in the radial phase, IRY, and that will be VRY over ZRY, and that is 400 angle 0 divided by 25 angle 53.13, and that gives you the 16 at angle minus 53.13. All right, so that would be the phase current, but the current supplied by the alternator now would be a line current, so it would be coming down on the line here. So IR. So what I really need now, I only need the magnitude because they had asked for line current for the current supplied by the alternator. They weren't asking specifically for what each phase was doing. Each phase actually has the same magnitude, but they would be at different angles. All right. So what I did was to find the line current, and you know line current is equal to root 3 I phase for a delta system. All right. So we know the phase current, so we want to find the line current. So IL root 3 I phase, which will be root 3 times the magnitude of IRY. So that's how you get the 27.71. All right. So that's the line current. So IR, any one of the line currents, them would have that magnitude, the 27.71. All right. Now, the part B of the question asks us to find the output and kVA rating of the alternator, neglecting any losses in the line between the alternator and the load. So it asks, it says that there are no losses in this line, in the lines here, between the generator and the load. So assume that zero resistance is here along these lines. That's what it's asking it to do. All right. Now, to find since there are no, to find the power output of the generator, we need to find the load demanded by the power demanded by the load. All right, so we go about now finding that power. All right, so the three-phase load, so it's 3V phase I phase cos theta P, right? And then using the data that we had worked out before for the red yellow phase, it's 3VRY times IRY cos theta VRY minus theta IRY. So it's 3 times the 400 times 16, because IRY is 16. Then the cosine of 0 minus 53.13. So that gives me.
So I don't understand why you use the line voltage instead of the phase voltage.
But it's a delta system,
Okay, okay.
isn't it? So the voltage for the delta system is a phase voltage too. Line voltage is a phase voltage. All right. All right. So we're working on this premise that whatever the load demands is what the generator supplies, since there are no losses in the line. All right. So what we do, find what the load is demanding, and then we can answer the question whatever about what the generator is supplying. You with me? With me? Everybody?
Yes, sir.
Anybody?
No, sir. Repeat that again.
Repeat what?
Um, the last part about what the generator is supplying.
All right. The question asks us to find the output of the generator, right? Output of the alternator. All right. Now, a generator will supply what the load demands plus any losses, right? So normally the lines will have some losses, right? So you would have been aware of that, Mr. Bruce, from Power Systems 2, that the line will have some losses. So the generator will supply the load demand plus any losses in the system. With me? Everybody?
Yes, sir.
All right. Now, they tell us that you should neglect any losses in the system. All right. So we're going to think of the losses as being 0. So any loss on this line is 0. Any loss on this line is 0. Any loss on this line is considered to be 0. All right. So the generator will then supply what the load is demanding. So what we need to do is to find the load demand. How much power is the load demanding? All right. And the load is a delta connected load. So 3V phase, V phase here. VRY is a phase voltage here. Although it's a line voltage, our reference phases are always phase voltage. Right. No, I'm not following the question then. Okay. All right. So basically, what I've done here in this first line is to write the general formula for power. 3V phase I phase cos theta. Right? So that's what I'm doing here. And then I use in the phase values. So although VR, Mr. Bruce, although VRY is a line voltage, it is also a phase voltage for the delta. All right. So when I put in the numbers, I end up with 11.52 kilowatts.
I give you the opportunity to scroll by in case.
All right. So since there are no losses in the line, then the output of the generator is equal to the load demand, equal to 11.52 kilowatts. All right. And then the upper end power is 3V phase I phase. And the I phase is a conjugate. It's 3VI conjugate, so I conjugate. Um, you probably remember from maths. So the conjugate of an angle would be the negative of that angle. With me? Because all right. So why this is important now is because the angle for an inductive load is positive. The S angle for an inductive load is positive. So if we had used a minus from the current, would have a minus angle here. So it's actually the conjugate that you should use when you're finding the apparent power.
Yes, sir. I remember something like this from networks too.
Right, 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 right. Okay. All right. So S equal to 3 VIP conjugate. So it's 3 VRY IRY conjugate. So as I said, the conjugate means that you multiply the the angle that you had before by -1. So this works out to be 19,200. This becomes a positive angle here. So you add these two angles, it becomes 53. So 19.2 at angle 53.13. You could have found it also by dividing what the power by cos theta, right? By the power factor. But in this case now you wouldn't see the angle. But you would know what the angle is from here or from here. So you could easily find it without doing this too. But the people who are doing power systems, electrical power systems, will be using the VI conjugate very often. And I want my machines 1 students to know it also. S equal to P plus JQ. You would have to go and find Q next. And you don't really need to do that. Remember, P is equal to S cos theta. So 3 VP IP is the S, you know. So if you have the power and you have cos theta, you can find S easily, which is what we're doing here, so right? S is 3 VP IP. So power, remember, power is equal to S cos theta. All right. Any other questions on this? On question 2? No? Everybody clear?
Yes, sir.
Sorry, can I scroll up a little? Yeah. So up here, so it's a power is equal to S cos theta P, right?
Right, right.
But S is the VI conjugate.
Right.
But at the top, S is VI without the conjugate. Does that make...
No, man. So the angles are here. So we still account for the angles, you know.
Okay.
We account for the angles here still. I'm just, when I write it like this now, you can see exactly that the angle for the right angle. I mean the correct angle for S when we do the VI conjugate. All right. But as I said before, if you divide this number by cos theta, you would get S also. So if you divide 11,520 by cos theta, cos of this is I think about 0.6, cos of 53. Right, 0.6. So if you divide the 11,520, you will end up back with the 1920. All right, so I mean, I'm basically pointing out different ways of doing the same things, right? So what you need to do is to become familiar with impedance triangle, power triangle, and the different ways you can find S. S is all. Somebody asked about Q a while ago. If shouldn't he have found Q? As you can see, it would have been unnecessary. Unless they ask you for it in the question, you don't need to go and do that. All right. So the idea is that you should now have a bag of tools to solve any three-phase question, and then you should know, be the good carpenter, to know which tool you must pull out when you need to do what. Okay. So, for example, you don't go for a Phillips screwdriver if it's a flat you really need. All right. So, basically, I have introduced you to all of the different tools that you can use to solve the problems. And then you will choose the most appropriate and the most efficient way of solving the problems. All right. All right. Question 1. Question 1 is, somebody said they didn't know how to draw the diagram. All right. So they tell you what to do, you know. So in fact, you probably could draw 2 diagrams because they have told you 2 things to do. All right. So they have a 3-phase load, a 3-phase motor, and they have 1 watt-meter. And they are going to try to find the total power drawn by this watt-meter, by by this motor using the 1 watt-meter. All right. Everybody with me so far? The motor is drawing a load.
Yes,
We have 1 watt-meter, and we're going to use that 1 watt-meter to find the total power drawn by the motor. But they tell you how they do the connection. All right. All right. So they say that the current coil of the wattmeter is connected in the yellow line. All right. So we have it in the yellow line. All right. Then they say we must calculate the wattmeter indication when the voltage circuit is connected between the yellow line and the red line. So the voltage circuit now, I show the voltage circuit being connected between the yellow line and the red line. So this would be where I get my first reading. All right. So I need to find IY and I need to find VYR. Everybody with me? So that would help me to solve the first part when the voltage coil is connected between the yellow line and the red line.
Sure.
Yes.
I ask you, I know it is VR and not VRY.
But because they tell you where the current coil is, right? So the current coil, if the voltage coil is going to be connected between there, the voltage coil is going to be connected where the current coil is. The positive end of the voltage coil is going to be where the current coil is connected also. I have two very small dots here that indicate the polarity mark. But wherever the current coil is connected, that would be the positive polarity for the current coil and also for the voltage coil. You with me?
Yes, sir.
All right. So it's VYR. All right. In part B, them say the voltage coil is connected between the yellow line and the blue line. So that time now, this would be moved and put here instead. The voltage coil will be switch around and put down to the blue line. And that time now, you'll be measuring VYB in that case. All right. Again, if you're not told what kind of machine it is, you assume a star connection. Right. Kind of easier to work out. Because in this case, line current and phase currents are the same. All right. So star connected machine assumed V phase equal to VL over root 3. So it is 400 over root 3, 230.94. All right. And then we define our reference phase as VRN. So VRN is 230.94 at angle 0. And then consequently, since we're using the red, yellow, blue sequence, VYN would be at 240 and VBN at 120. Now we need VYR, so I'm calculating it right away. So VYR is VY minus VR. So it's 230.94 at angle 240 minus 230.94 at angle 0. So I end up with 400 at angle minus 150 or 400 at angle 210. So same thing, right? And since I know I'm going to need VYB, I calculate VYB also. So that's VY minus VB. And I get 230.94 at angle 240 minus 230.94 at angle 110 degrees. All right. So that gives me the 400 at angle minus 90 or 400 at angle 270. Same point. Right? So now that we know the
Sir,
we know the vote. Yes.
so give us a few seconds to write that, please.
Oh, all right.
So, sir, so VYR and VYB magnitude is basically the same thing as the line voltage.
Yeah, they are line voltages.
So you calculate that just to get what the angles.
Right, right, right. Very good. We need the angles when we're working out the power.
All right, sir. Thanks.
All right. All right. So we have the voltage data. All right. Let's look at the motor data now. So the motor, they tell you that the output power is 15 kilowatts, has an efficiency of 88% and a power factor of 0.84 lagging. All right. So I've put that information here. All right. So I found the angle now for that lagging power factor. Now, when it's lagging for current, is a minus. You need a minus sign here, right? So a minus cos inverse angle. So the angle here is minus 32.86. All right. So remember, lagging means that the current is lagging the voltage. All right. We're given the efficiency 88% and R 0.88 per unit. And efficiency is power output over power input. So therefore, power in is equal to power out over efficiency. So the input power is 17,045.45 watts. All right. Now we can find the current from that. All right. What I've done is use the line, the formula for line. Where am I? Using the find the power using the line parameters, line voltage, line current. I can do this because it will give me a little bit more accuracy because I'm not writing 230.94, which is actually rounding off. So I do that, but still you will find that there is still maybe some slight errors because of rounding off. All right, so IL is P in divided by root 3 VL over cos theta. So I find the magnitude of IL. All right. And the magnitude of IL is equal to the magnitude of I phase, since it's a star system. I line equal I phase. All right. I found IR, but I didn't really need to find it. The only one I really needed to find was IY. All right, so working mechanically, I found IR. So IR would be lagging VR by 32.86 degrees. So that's why IR is this, right? But as I said, the question had only one current of interest, IY. The current coil is in line in the yellow line. So we only need to find IY. All right. So IY lags VY by 32.86 degrees. So IY is the 29.289 angle 240 because VY is at 240 minus the 32.86. So I get IY to be 29.289 at angle 207.14. All right. Everybody okay with that? Yes, no, maybe?
So when you get the IR logging value, yeah, the 32.8 logging missing.
Look again.
It's inverse of the wow.
Okay.
You're given that in the problem, right? You're told that is a lagging current too. So it will be lagging. So in this case, it's lagging VRs and VR is at angle 0. So IR would be at angle 0 minus 32.86. So that ends up to the minus 32.86. IY similarly is lagging VY by 32.86. So IY is at angle 240 minus 32.86. So it ends up at 207.14. All right. Now, the first reading that the wattmeter had was when it was reading IY and VYR. So put that in my equation for the power that the wattmeter is reading. VYR times IY cosine of the angle for VYR minus the angle for IY. And put in the data 400, 29.289 cost. Remember, VYR was at 210, and this IY is at
So if
207.
you have the negative 150, so it's the same thing, right?
Yeah, it wouldn't really matter. All right. And so the power that the wattmeter first read was 11.7 kilowatts, or 11,701 watts. All right, everybody okay with that so far?
Look, I do my one back here because I don't get 52, or that doesn't matter.
No, man, it matter. It matters because the angle is going to be different. So let's look at that still. So the second reading, second wattmeter is second reading of the wattmeter is when it was reading IY and VYB. So the voltage coil was switched now from the red down to the blue line, right? So it was reading VYB and IY. All right, so the formula then is for wattmeter 2, VYB IY cos theta VYB minus theta IY. So 400 times the 29.289 times the cost of VYB is at 270 and IY is at 207.14. So the second reading of the wattmeter then is 5,344.26 watts. When you when you add them up now, you get the 1705, um, and the decimals them are a little bit off, but we know so it's probably it's more due to rounding off really. All right. So all right. All right. Any other question on this?
So, sir, the diagram you drew would be considered a phasor diagram.
No, no. Phasor diagrams are
Yeah, showing angles and stuff, right?
right. Remember, phasors are practically vectors, so they have magnitude and angles. So this is nowhere near a phasor diagram, but you can use these now. So you can use these values for the voltage, both the phase values and the line values, to draw your phasors. All right, so you just basically put them on hold on there. Yeah, you just basically put them on a graph sheet.
The question said with the aid of a phasor diagram, calculate wattmeter indication and so forth. So.
Right. So you need to know how to draw your phasor diagrams. Right. You really need to know how to do it. The textbooks will show you a whole heap of phasor diagrams. They might not necessarily draw it. Use the same reference. Their reference starts up at, for some of them, up at 90 degrees. I don't use that. My reference is at 0 degrees. Right. Which is what we use from maths. You guys finished with this? All right, so you finished with this page. All right. All right, so a phasor diagram will require a ruler and protractor if you want to draw it very accurately. Most time you're gonna draw the lines them to scale though, because you can with some of the voltages that you have, you will have to draw them to scale. But the angles need to be accurate, are fairly accurate. So when you're doing your phasor diagrams, you need ruler and protractor. All right. Well, we're practically finishing them, but let's see something here.
Sir,
Yeah.
the last question that we did in yesterday's class, well, you gave us a second part of it, sir. Could you go through that, sir?
All right. Tell me, what did you come up with?
Sir, because my stuck said I asked you.
Oh, what was the question again?
Yeah, right there, sir.
So, did you find these currents?
Sir, something that confused me was because it says the magnitude for the line current, sir, and I was wondering if we need like all the individual line current or one could substitute for all, but yeah,
It's
that was
one. All right. So, I want everybody to understand it. Since it's a balanced load, there's a 3 similar coils, right? So the load in each phase is the same, right? So the phase currents all have a particular magnitude. Let's say the magnitude is 10. I don't remember what it was for the phase currents. Oh yeah, I can go back.
yes, sir. Well, 75.63.
Right. So the phase currents were 75. It's a delta connected system, right? Right. So the line current then would be just root 3 times that, right?
Okay.
130,
Okay.
Times the
130.9.
magnitude.
You get 130.99.
Okay. I would have to go back and look and see where I wrote it down somewhere. But yeah, it will be root 3 times the phase current. Um, so what I wanted you to do was to all right. So before before we put in the capacitors, this was the power drawn, right? The apparent power. Everybody with me? Before we put in the capacitor, the apparent power drawn was 90.76 kVA. All right, 90.76 kVA. Now remember, S is equal to root 3 VLIL. Everybody with me? So I can find the magnitude of the current from that. S is equal to root 3 VLIL. We need the line current, so just divide this value by root 3 times 400, and I will get that current. So, all right, so somebody work it out for me now.
So it should include the angle, right?
No, you don't need to use it. Remember, as I'm saying now, since it's a balanced system, you don't they didn't ask you, they asked you to find the magnitude. All right, so when they say magnitude, they don't want the angle. Even if you find the angle, it wasn't required for that particular question. Clear?
So the questions you're working, sir? Part what?
Say that again.
Yeah, at part what in the question?
Part one. So we're looking at it asks you to find the line current before power factor correction.
So wouldn't it just be or you giving us a different way to work it out or something?
Yeah. So right. So you can go back to the apparent power. S is equal to root 3 VLIL. Or since you had found the phase current before, you just multiply that by root 3.
Root 3. Oh,
Okay.
Yes, sir. When I
okay.
do it the apparent power method that you just tell us, I
Yeah.
got 131 and it was close to the 130.99.
Okay. Right. So again, remember now that you have different ways of working out these things. So um, just use the most appropriate one, right? So yeah, 130.99 was the line current before. So that would answer part one here, and then we need to find the line current again after power factor correction. So what we do, the easiest way to go back now is to find what S
The
was.
apparent after and then
Uh,
divided by root 3 times 400.
right. So it is the 80.754 kVArs divided by root 3 times 400, and you would get a. Let me see what that number would be. Yeah, try work it out now. So it was what 80,753.661. So I think it comes down to 116.56. So it moves from 131 down to 116. Clear? Everybody? Just divide this number by root 3 times 400, and you will find what the new line current is. All right.
Current decrease.
Right. So that was a question now. State any benefits you see of power factor correction. And one of them is that the line current has decreased. And just like what we discussed a while ago, that if the line has resistance in it, and lines usually have resistance in them, the losses will decrease along the line. All right. So that's one benefit of the power factor correction. You have reduced losses on the line. So that ends up making your system a little more efficient. All right. What I want you to do is go and research benefits of power factor correction. You can find them in the textbooks. All right.
Sir,
Yeah.
okay. Quick question. If you do power for like 4 years, you would suggest drives to over like project man.
Become exhausted too bang in headless.
Yeah, man. You want to know drives too? If you're specializing in power, yeah.
Alright, drives to.
No, I wouldn't say that. I wouldn't say that.
Something I forgot, you know. Something I forgot.
Well, yeah. I mean, so right. If you are going to be doing power, you need to have drives too also, because we're going to be going more in depth now in the machines, motors and generators.
So it would be like power systems, power electronics, renewables, and drives to, basically.
Yeah, something like that. Yeah.
That's how they run at the. Alright, so that's how the power combo.
Okay. All right. I think the 6 o'clock people are joining us now. Yeah. No, I'm not saying that. No, you decide that. But I'm telling you what you need.